Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, is that a robot astronaut? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is about autonomous robots in space, with a guest whose ambition to solve the astronaut labour bottleneck with robotics and AI is close to becoming a reality. Before that, this is your regular reminder to support the podcast by signing up as a paid supporter on Patreon. Not only will you receive my eternal gratitude for helping the podcast to continue, but you'll also get access to lots of cool perks, including monthly bonus episodes, behind-the-scenes updates, merch discounts, and more. Check out patreon.com/Claire Asher and join the Robot Talk community today. So, with all that said, it's time for me to introduce this week's guest. I recently had a fascinating chat with Jamie Palmer from Icarus Robotics about building a robotic labour force to perform routine and risky tasks in orbit. This week, I'm chatting to Jamie Palmer, co-founder and CTO of Icarus Robotics, a company developing a robotic labour force to perform routine and risky tasks in low Earth orbit. Hi Jamie, I'm excited to have you on Robot Talk.
Thanks for having me. I've been looking forward to this one.
So, you co-founded Icarus Robotics last year, and you've already been very successful in raising funding for your mission to address the labour bottleneck in space with robotics. So, how do you plan to make that ambitious goal a reality?
Yeah, so making robots is already a pretty hard task.
Yeah.
Making them for space is even harder again. So the reason why we started Icarus is kind of really important to us. So ultimately, what we're building is these free-flying dexterous mobile robots. And what that means in sort of plain English is imagine like a free-flying drone with robotic arms on the front that is basically mobile in microgravity. So it's essentially floating in microgravity. And we're operating inside space stations, working alongside these astronaut crews to help them with the sort of, like you said, menial and sort of time-consuming tasks. But this is particularly important because an astronaut costs, believe it or not, $130,000 an hour just to keep alive in space. So that's the sunk cost of having the crew to support them, the life support systems, everything that goes with it. So getting humans to do work in space is really, really expensive. And it's not that the astronauts taking that home, although I wish they were. But ultimately, what we're doing is we're building robots to assist these astronauts. So there's some very, very time-consuming tasks like unpacking cargo. You get 3.5 tons of cargo coming up on resupply missions every 30 to 60 days on the ISS. And essentially what we're doing is building these robots to assist them. So in terms of how we can actually make this a reality, so I think one of the first things that was really important is myself and my co-founder Ethan spent a lot of time early on talking to everyone in the space industry, trying to figure out, what are humans actually doing in space? And what does this actually look like? What are the tasks? Where's the time going? And where is the real value created? And what we learned is that, one of the most valuable things that humans can do in space is this amazing science and experimentation and some really, really sort of difficult and dexterous tasks. But they also, as a consequence of going up there, also have to maintain their vehicles, maintain their habitats, and do a lot of this sort of work. It's quite challenging. So we talked to astronauts, we talked to the ops planners at NASA, we talked to folks that have put experiments on the ISS, folks that are running the next generation of commercial space stations, and ultimately tried to figure out, okay, if we were to place a robot here to help these people out, what would that actually look like? So that was kind of the first step. Then afterwards, like you said, we're kind of fortunate to raise the funding round. So we raised $6 million just about this time last year. So it's been just about a year now. And then we had the capital to actually go and start developing these robots. So one of the first initial things that we did to sort of prove out that we could do this was we built a remote teleoperation system. So we actually unpacked a NASA cargo bag from our office here in New York to California in real time over 2,500 miles to demonstrate, okay, remote manipulation is something that's feasible. We're doing it on a task that seems to be high value for NASA and these new future commercial space stations. So this was kind of the first step.
Yeah, that's
and
cool.
The second step to kind of making it a reality was going and actually building a full free flyer and actually testing it in our office. So myself and our founding engineer basically developed this full, very, very simple sort of prototype of this free-flying mobile robot, and we were able to control it remotely. We were able to do some local testing, and then we kind of keep building in fidelity to there. To now, to where we're at the point where we're building our Joy V3 robot, which is a much more sort of complex free flyer that we're preparing to fly on a parabolic flight. So we use a mix of terrestrial testing. We use a mix of things like parabolic flights.
It's the colloquially known as the vomit comet, right?
The vomit comet, exactly. Where you're going to get the plane in the sky diving at the same rate of gravity. So you're getting these small microgravity periods where you can actually test, for example, a free-flying robot. And then leveraging things like simulation, leveraging things like terrestrial tests, like our air-bearing facility that we have here in the office, which is a 2D big planar surface with a chassis, with some air bearings. You can imagine it as a really complicated hockey puck that we put our robot in, and we can basically do testing in 2D microgravity as well. So I guess a mix of sim, a mix of big tests like the parabolic test, and a mix of the terrestrial tests like the air-bearing table. And that's kind of all the things that we're doing to get ready for our first space mission in 2027, where we're going to the ISS with Voyager Space to basically, work alongside the astronauts, which we're really excited about. And it's our big North Star at the moment. So
that's really cool. Yeah, I was going to ask, like, how different are the considerations for flying a robot in microgravity? I mean, if I remember correctly, on the ISS, they still have like 90% of Earth gravity. It's not as people think that there's no gravity up there at all. Like, that's the kind of way we imagine it. But the reason that you float in the ISS is just because it's essentially constantly falling, right? This is now the limit of my knowledge about the ISS.
Yeah, so we call it microgravity because I think the percentage of gravity that you would experience is, I'd say, approaches zero. I guess it's all relative, really. And this idea of you're constantly sort of falling towards the Earth, that's, I guess, the ISS staying in orbit. But then the actual relative experience that you're going to have when you're in the ISS is that you're basically free floating with respect to the world frame. So ultimately, you are experiencing like a true sort of zero gravity environment. But I guess throughout the whole universe, there's gravity everywhere, right? It's just about how much we feel it relative to our frame. So.
Yeah, I suppose the robot is experiencing the same forces that the astronauts are. So yeah, obviously you're making it and testing it on Earth. So a lot of the same design considerations must apply. It's not a completely different design spec for a robot in microgravity.
Yeah, so because we're deploying to the ISS first, the thing that's really exciting and interesting about that is that you don't have to deal with the radiation hardening to the same rate you'd have to do if it was in the vacuum. You don't have to deal with the temperature extremes. So the way that we kind of think about it is it's really not dissimilar to deploying like in the room that I'm in now. The only difference is there's no gravity in that room. So we're actually able to pull on different COTS components. We're able to do a much faster ramp towards actually getting a robot ready because we don't have to go through years and years of qualifying this thing for the vacuum. I think the one thing that's challenging about it is the idea of this is a free-flying robot. There's been some successful free-flying robots in the past. Japanese Space Agency made one. NASA made a really great one called Astrobi. And the German Space Agency made one as well. And I think these have all been recently operational on the ISS. But the core thing that we're doing that's different to what they've done is we're adding manipulation capabilities. So now our robot can actually do physical work. But what this means, which is much more challenging, is now instead of trying to propel this rigid body through microgravity, instead now you have this big kinematic chain of actuators. You have this big 20 degree of freedom system. And every time you move one of the arms or you kind of extend them out or push on something or grab something, you have no damping. So you're going to get an equal reaction force back. Course, so now all of a sudden controlling this base becomes very, very challenging. And it actually becomes much closer to, say, controlling an underwater robot because, you still have that reference frame. But in an underwater robot, oftentimes the buoyancy and the gravity are fighting each other. So yeah, I think it's quite a complex problem, the flight control, but it's a really exciting thing to get to build.
Yeah, really interesting challenge. So your background is in robot dexterity. You previously studied at Columbia University in the Robot Manipulation and Mobility, or ROME lab, and during the pandemic worked on autonomous hospital robots. So I'm particularly interested in robot dexterity. I was wondering if you could talk a bit about some of the recent developments in that field that you can leverage now for space applications.
Yeah, I think it's been so exciting recently in dexterity, because locomotion had its moment for sure, and we've seen the sort of things that Boston Dynamics could achieve doing kind of like parkour demonstrations and stuff like really early, even before we were doing really heavy ML stuff. In dexterity, some of the really exciting things that got me really interested in it were like some of the more recent research publications that have come out. The biggest one for me was Google RTX. This was huge. Okay. The OpenX embodiment project, where they were able to take data from different manipulators, train a really large manipulation model, one of the biggest manipulation models that had been trained at the time, and then actually essentially do many different diverse grasping tasks across also many different pieces of hardware with the same model. So A, being able to generalize across many tasks, and B, being able to generalize across multiple hardware embodiments was just mind-blowing to me. And I think that was the real moment where I realized, okay, general purpose robots are actually really going to become a thing. This is actually, there's something really meaningful here. I think some other things that I thought were really interesting as well that coincided with us starting the company, where there was a piece of research done called Open Television. And for the first time, we saw really, really good high dexterity teleoperation at really long distances. So basically, the whole premise of Open Television was there was an operator on the East Coast of America, and there was a humanoid on the West Coast of America. And you were doing real-time dexterous control of this humanoid using pose mapping and stuff like this to do high dexterity tasks in real time at a massive distance. And that showed me that, okay, in actual fact, remote manipulation, teleoperation, this is actually a really useful technology that could perhaps actually have a really, really big impact. So it's very good doing it from coast to coast, but this now enables you to go to some of the most distant regions, whether it's the bottom of the ocean or, in our case, space. Now, there have been great examples of teleoperation before, but I just thought that one was particularly impressive, and it's a more recent piece of work. And then finally, I think one of the biggest things as well has been the idea of physical intelligence, so Pi 0, Pi 0.5, where again, we've seen now long horizon tasks being done by these robots, really high dexterity, things like folding laundry and actually putting it in the laundry machine and closing the laundry machine and setting it to go. Things like, bussing a table where you can basically take all the dishes, pack them into a cart, move them, and then clean the table afterwards. We'd never seen anything so long horizon before. It was amazing.
Can you explain long horizon? I think I intuitively understand what you mean from the context, but if you could define that.
Of course. So a short horizon task might be, perhaps I have my mug in front of me, and a short horizon task might be to move that from A to B. A long horizon task could be something more like a human would carry out. A multi-step task, say, for example. So unload the dishwasher is a classic one. It's not just grab one thing and take it out and move it to another place. It's actually grab many things and understand how the scene is changing, and then understanding when the task is done, and then doing any additional actions to close it up. So long horizon being the ability to kind of do those longer multi-step tasks.
Yeah. Okay, cool.
But I think what the most exciting thing about all this was looking at what are the implications then of these pieces of work for general purpose robots. And what became very clear to me is this framework of learning from examples, which all these pieces of work have done so successfully in different ways. So now we can actually go and have a human do remote teleoperation in real time and, collect what we call expert examples. And then we can use these expert examples to train amazing models or policies, like, your Pi Zeros or like your Google RTX models, where you can now actually train learned autonomy for manipulation, which I think is just really, really exciting and opens up so many avenues. So I think it's that two-part piece of starting with remote controlled robots, starting with that teleoperation, and then using the expert examples to train the future autonomy. I think that's the kind of really interesting pipeline that I saw there. And that's something that we're definitely going to apply to space. So we're starting off teleoperated, and then we will be using the expert examples that we get in the microgravity environment to train one of the first ever microgravity manipulation models.
Amazing. So what in-orbit tasks do you think these robots will be really well suited to? And what things are, at least for now, best left to the astronauts?
Yeah, there's a great split between these two. In terms of tasks that would be appropriate for the robot to do, how we basically discover these is by talking to the ops planners, talking to astronauts and these folks that run these habitat stations and infrastructure. What we realized is we basically went through and tried to find the biggest time sinks. So the first biggest time sink was cargo resupply. So again, every sort of 40 to 60 days, you're getting 3.5 tons of these standardized white cargo bags. They're kind of like gym bags. Okay. And basically what an astronaut has to do at this 130K an hour price point is unzip the bag, take the items out, put the items away, stow them, rezip the bag, stow the bag. And imagine doing that for 3.5 tons of cargo. So it's taking, it could take 2 weeks basically. So that was one of the first things that we've seen. This is a task that is kind of like dull, repetitive, where the human doesn't necessarily feel that they're adding any new value, but has to be done and takes a lot of time. So that's a really good example of a task where the robot should be doing it. And also what we've looked at as well is the robot doing things like visual seal inspection, which is a high frequency task, but again, just time consuming and repetitive. There's other tasks as well around this where, you have a similar thread where the task is kind of either, the standard dull, dirty, or dangerous. So that's the ones that we're looking at initially. And all these tasks are, I guess, internal in the space station. In the future, the ones that would be appropriate for a robot are work outside of the station so that you don't have to send the human outside, which is so dangerous, so expensive, and so time consuming. So things like maintaining the stations, things like maintaining large satellite fleets, things like maintaining, we're seeing orbital data centers becoming very serious for the first time. So all this infrastructure that's going to go into space, in the future, we want our robots to build and maintain them. But we're starting off with that beachhead of the space stations. In terms of what's good for an astronaut to do, I think this is even a much more interesting question. So I think very, very high dexterity tasks that also need a very, very high level of intelligence are the ones that you really want the astronauts to do. So things like actually running experiments, doing science, things like this are very, very difficult for a robot to do. So ultimately, these are the things that we want the astronauts to do. But also there's another bit where there's tasks that the astronauts like, is a bit of feedback that we got. So there's certain tasks that you actually really, really don't want to take away from the astronauts because they really, really like them and you want to leave them with the things that they like. They're already remote, far from home, far from Earth, far from family. And they're already doing amazing work for humanity. So you leave them the things that they actually really like. And one of those things we got as an example before was they really like watering any of the plant habitats. Okay. So that was a really interesting thing that we learned last year that we thought was very cool. So you won't see an Icarus robot watering a plant in space anytime soon.
Yeah, that's interesting that that's the task that they enjoy. I guess when you're that far away from Earth, interacting with another living thing is probably quite therapeutic.
I bet.
So, even the best robots sometimes have mechanical issues. They need maintenance. Obviously, you don't want to have to bring those robots back down to Earth to do that. Mm-hmm. So, will those astronauts need to have some kind of basic robotic maintenance skills so that they can actually look after this labor force that's up there helping them?
The way that we think about the astronauts and how to design such that they can interface with these robots is quite interesting. So the astronauts are very, very, what I would call very competent, very skilled non-experts. Yeah. So most of the time, the astronauts, their backgrounds are some sort of really, really impressive military background or medical background or science background or engineering background. So very, very amazingly competent people that are very, very skilled. But again, like you said, they might not be an expert in robotics. So what we're thinking about when we're developing this robot is any of the sort of major components and any of the sort of major parts that may need swapped out or may need some attention. We're trying to think about how do we make that as modular as possible, so that it's really, really easy to swap and replace for anyone with any sort of basic mechanical intuition. So how can you make your arms easy to swap in and out with just a simple bolt pattern and a very easy modular connector for data and power? Similarly, the drone motors, how can you have like simple to swap out assemblies that maybe encompass a lot of the components where it's more of a plug in, plug out sort of operation rather than, taking out the tool set and undoing, 28 fasteners, like 2 seals and something else. So that's how we kind of think about it, is how can we make these as modular as possible such that these very skilled and competent non-experts can actually go and replace any core components if they need to. And I think a really exciting future would be if the capability of the robot got amazing, we could have the robots repair each other, which I think would be quite nice.
Yeah, that would be really cool. So, I mean, it seems like you're currently on this amazing journey of, developing your robot, building your company. What has been the most fun so far?
A lot of it's been really fun. A lot of it's been really hard too. But
yeah.
I think what I like the most is, I never really understood what this meant before I started a company. And I thought it was kind of a buzzword, was this idea of culture. But actually, I think one of the things that I enjoy the most is actually just like being up there with my co-founder, with my team, and actually getting to work on this really, really hard problem. And because, we started this company and we've kept it sort of, we haven't brought in a load of procedures and a load of policy and a load of stuff like this. And we're still young and early and hungry. That it's a very, very exciting environment to be able to build robots in. And I just love the freedom of, you can actually, in an environment like this, you get to experiment, you get to try things, you get to build new robots, and you get to try to do something that nobody has done before, all while doing it in a room full of people that, you're really happy to be with, that you really respect.
Yeah.
And that you really sort of enjoy working alongside. So I think it's been very different to anything I've ever done before. But I think that's been the most enjoyable part, is you kind of get to really, really shape what it looks like and actually do the core work that you really care about with the people that you think are, the absolute best.
Yeah, definitely. A thing I hear a lot from people who work in robotics is that feeling when it works, when the robot moves, in the way that you've designed it to, is like the best feeling in the world. I imagine the feeling when you get that robot moving on the ISS when you're here will be incredible.
Yeah, I've thought a lot about it. I think about it very, very often, about what it's going to be like and what that's actually going to look like or how that's going to feel. I think there's like two big milestones that I'm kind of really looking forward to, obviously, of course, nervous for, but is that the first rocket launch. So when it goes up there, and then that time afterwards, which will probably be like a couple of months before we actually have our test window and it gets booted up by the astronaut and we connect to it for the first time and we see the heartbeat for the first time, and then, it's actually real. And I think that's just going to be such an incredible experience. And I think thinking about something as visceral and as strong and almost emotional in a way as that is a really good motivator on the sort of long days. And when it does start to get a bit tricky or when things aren't quite going right, you can think about something like that. I don't think you need any other motivation other than thinking about that day. So I think it's quite exciting.
Yeah, absolutely. Well, I will be watching your company's progress with excitement and anxiousness, hoping that it all goes well. Jamie, it's been great talking to you today. I've been speaking to Jamie Palmer from Icarus Robotics. Thank you.
Thanks so much. I really enjoyed it.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. And check out @RobotTalkPod on social media to see a photo of Icarus Robotics' latest robot, a semi-autonomous, teleoperated, free-flying drone. Next week, I'll be talking to Maria Guix from the University of Barcelona about miniaturized living robots. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.